Another interesting wave phenomenon is called beats. We've talked about superposition a few times. We thought about constructive and destructive interference. We had to superpose some waves for that. And in that case, the waves had the same frequency. We thought about standing waves. That was superposition of a wave going this way and a wave reflecting back this way. And there they had the same frequency. So beats are different because it's superposition of waves with different frequency. And this makes something special happen. So first we'll look at it. So I'm going to plot some waves for you here. And here are two waves that have what looks like the same frequency, but they're actually slightly different. So we're doing two waves with a fast frequency but a small difference. And you can actually tell that here they're in phase because here is the peak is well aligned with that peak. The top and the bottom have their peaks well aligned. But then if we go down the wave, you get to a point where the peak is well aligned, of the bottom one is well aligned with the trough of that one. So here they're out of phase. But then if you move along here, they're well aligned again, right? This peak is aligned with that peak. And the reason they're going in and out of phase is because they have different frequency. Right? We're plotting them along and one is going a little faster than the other. So they go in and out of phase as you go along. So now let's put them on top of each other. And you can see that, as I just said, these two add in phase. They're right on top of each other. And if you go a little further down, now they're out of phase. And then they're in phase and out of phase, and in phase and out of phase. Well, you know what's going to happen when we superpose things that are in and out of phase. In phase, they're going to add. Out of phase, they're going to cancel. So let's plot that. And like we just said, in phase, they add. In this little region out of phase, they cancel. Right? And this is what makes the beat. The results of adding them makes a fast frequency that's about the same. It's really the average of the two original frequencies. But then it's modulated by this slow sinusoidal shape, like this. And if you make this a sound, what does it sound like? It goes wah, 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 right? So beats say wah, 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 apparently. So now I'm going to let you listen to some beats. So two speakers. This one's at 200 hertz, and this one's at 200 hertz. So let's turn them up, right? There we go. Now I'm going to increase this one to 202 hertz. And there you hear the beat frequency. It sounds like it's at about 2 hertz. It sounds like it's at the difference of the two sinusoids. Let me increase this one to 204 hertz. Whoop. So there you can see the beat is faster. Again, it seems to be the difference. Now let me decrease this to 198. Right? This is 204. Turn this down to 198. That speeds it up even more. It's really the difference between the two frequencies that matters. So now we're up to about a 6 hertz difference, and it sounds like about a 6 hertz beat. Okay, so that's what they sound like. You've probably heard this before. When you're on a plane, sometimes when they're revving the engines, they go at slightly different frequencies, and you can hear the engines go whoa, 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 and you think, ee, okay. One interesting thing about beats is that the frequency actually doesn't come out exactly like it should. If you do it with your ear, you say that the frequency of the beat is equal to the difference in the frequency of the two sources. If you do it mathematically and you write an equation for it, you find the frequency of the beat is half the difference of the frequency of the two sources. There's a half in the formula if you solve it. And it's a little confusing, but the reason is actually pretty clear, is you hear 2 beats per cycle. So mathematically, the beat wavelength looks like this. It goes up, and it goes down, and it goes back to 0. So that's an entire cycle of the beat sinusoid right there. But how many beats do you hear in that time period? You hear 2. So since you hear 2 beats per cycle, and it's equal to half the frequency of the difference, the 2's cancel, and you actually do hear the difference in frequency, is the beats that you hear. So listen for beats in the world. I'm sure you'll find some somewhere.